In the class we talked about the spawn keyword. So you may recall that if we put this keyword before a function call, let's say a function foo, then this new function foo is called as a new sub process that can potentially execute in parallel to the calling process. So the calling process or the calling function doesn't have to wait for this foo to complete and return. They both can execute in parallel. The next keyword that we are going to talk about today here is the parallel keyword, which is added in front of loops. So for instance, if you say parallel, for just a second, let me fix this. So if you say parallel for I equal to, let's say, 1 to n, and inside this for loop you have some statements, maybe some print statement. So potentially each of these iterations of the for loop can execute in parallel simultaneously on n different CPUs if they are available. So this is what this parallel keyword means. So let's see with the help of an example from matrix multiplication how this might be useful. So let's say we have an n by n matrix A, and we want to multiply this matrix with an n vector x. So for example, let's say you want to do something like this. Let's say this is our n by n matrix. So let's say we have 1 2 3 4 5 6 7 8 9, and let's say this is the vector that we want to multiply it to. So let's say the vector is 10 20 and 30, right? So you all would know that basically we will multiply it, the first row will be multiplied with all of this column, right? So the first element here in the resultant vector would be 1 into 10 plus 2 into 20 plus 3 into 30. So this is going to be the first element, and then the second element similarly is calculated by 4 into 10, 5 into 20 plus 6 into 30, and so forth, right? So let's assume that this is our matrix A, this is our vector x, and this is the result vector y. So the ith entry yi in this resulting vector is basically given by aij multiplied by xj for j going from 1 to n. So summation of all of these products, and then we do this for every I going from 1 to n. So here is the code for multiplying our matrix A with input vector x, right? So for now, for to start with, let's ignore these parallel keywords, right? So let's not think about this. If you ignore these parallel keywords, the rest of the code here is the standard sequential code for multiplying this matrix A with vector x. Now remember that this matrix A is basically an n by n matrix, and this vector x is basically an n by 1 vector, right? So basically the resulting vector y would be an n by 1 vector, okay? Because basically we will ignore this the columns in A and the row in X, and the resulting matrix would be simply n by 1. So let's quickly go over this code. It's a standard code for matrix multiplication. So we start with finding the dimension of y, which is simply n. So we get the value of n by a dot rows, because a is a square matrix, so it has the same number of rows and columns. In the second line, we allocate space for this resultant vector y. In the next two lines, 3 and 4, here we are initializing this output vector y with 0, right? So basically if this is your y, let's say, that has 1 2 and so on up to n elements. So we are just initializing each of these with zeros, and then in these last I'm sorry, in these next three lines, 5 to 7, here we are doing the actual multiplication. So recall that basically the ith entry in this vector y is basically given by sum of a of I j multiplied by x j, and for j going from 1 to n. Basically that is what is happening in this loop over here. So this is the standard sequential code for doing the matrix multiplication. Let's now see how we can parallelize this, right? So let's start with this first parallel keyword over here. So notice that this first loop in lines 3 and 4, it is simply initializing each of these entries in the vector in this vector y with 0, right? So can this be parallelized? Well, is there any harm if, let's say, CPU1 is writing 0 in the first entry of this vector, CPU2 is writing the 0 in the second entry, and so forth, right? And let's say CPU n is initializing the nth entry in vector y with 0. So all of this can happen in parallel. There is absolutely no problem with that, and that's why we have added this parallel keyword in front of the first for loop, so that this initialization of each of the n entries in y vector can happen in parallel. Let's think about this second nested for loop over here in lines 5 to 7, right? Let's assume this is our matrix A, this is our vector x, and this is the vector y that we are computing. So let's compute the first two and see how that goes. So here is an example of computing the first element of y. So essentially what we have done is the first entry of vector y would be 1 into 10 plus 2 into 20 plus 3 into 30, right? So it's basically a of 1 1 multiplied by x of 1 plus a of 1 2 multiplied by x2 plus a of 1 3 multiplied by x3. So notice that each of the entries in this matrix y, in this vector y, are computed by accessing the values in input matrix A and vector x. So matrix A and x, they are accessed in read only mode. So because of that, would it be fine if we, let's say, compute the first entry, let's say this one on CPU1, maybe the second entry on CPU2, and the third one on CPU3? Can that be done in parallel? Well, it turns out yes, because these input matrices A and X, they're not being modified, they are only being read. And if we were actually computing the three entries of this vector y on three different CPUs, they would be writing on three different locations in this vector. So all of that can be done in parallel. So that exactly is accomplished by adding this parallel keyword in front of the outer for loop on line 5. Well, you might wonder, shall we also add a parallel here in front of the inner for loop, and maybe also further parallelize this second for loop in at line 6? Well, we'll come back to that one. So let's now think about the complexity of this matrix vector multiplication after we have added these parallel keywords. So notice that by default, if there was no parallelism, let's say this was a sequential code, then in that case, what was the complexity of this algorithm? So this line number 3 to 4, 3 and 4, this is a for loop going from 1 to n. So this is big O of n. Also, this is in line number 5 and 6, we have this nested for loop, and each of these for loops is going from 1 to n, right? So this is basically big O of n square. So by default, if you are executing this matrix vector multiplication function on a single processor, it is going to run in big O of n square time. So how would this runtime change if we now have, let's say, infinite processors, and we can execute this parallel version of matrix vector multiplication on all of these infinite CPUs? Well, it would improve, obviously, we will get some benefit of parallelism. However, it is important to realize that parallelism here basically means replication. So at time t equal to 0, let's say you started this parallel version of your matrix vector multiplication function on a single CPU, right? And when this function starts executing, at that point during execution, let's say the compiler realizes that these two for loops can be executed in parallel on several CPUs, and let's assume that our machine has infinite number of CPUs. It still takes some work for the compiler to replicate this function and copy it over on these several parallel CPUs, right? So every copy that the compiler does, or every replication that this compiler does to spawn this process in parallel, or this function in parallel on new CPUs, is going to take some finite amount of time. Okay, so whenever we are analyzing the time complexity, the runtime complexity of a parallel loop like this, we must account for how much time or how much extra work the compiler needs to do in order to replicate this function on several CPUs. So that is what we are going to look at next. On right over here, this is our code of matrix vector multiplication from the previous slide, and on the left over here, this is the code that a compiler may use for replicating this matrix vector, this parallel matrix vector subroutine on n number of different processors in parallel. So by the way, before we look into this compiler code, I just realized that in line number 6 over here, in this for loop, there should be a new keyword, right? So this should actually be for, here you should have new, right? So here basically you need a new keyword. Now the reason is this new keyword basically indicates that a new variable j should be allocated for every iteration of I of this outer for loop, so that different iterations of this outer for loop, they do not attempt to update the same variable j. That would be a problem. So later on we will see that may cause a race condition, right? So there should be new variable. I don't know how that got missed, so sorry about that. So let's continue here. All right, so we have seen that this parallel keyword here basically means that every iteration of these loops can execute in parallel, potentially on n different processors simultaneously. However, by default, when this matrix vector function this starts executing on the machine, it will start on just one machine. And we have seen that the compiler will somehow need to replicate these n iterations, right? These n iterations of each of these parallel for loops onto n different machines. So how can that be done? One possible way of accomplishing that is using divide and conquer approach. So let's assume that our for loop is going from index 1 to 8, right? Let's say this is our for loop in the original machine. So the compiler can recursively spawn, let's say, the first half of this range at every step, so that the first half of the iterations can execute in parallel with the second half of the iterations, right? And then eventually you will sync, so that both so that you proceed only when both the halves of iterations have finished. So essentially, for example, in the first step here, the compiler can spawn, let's say, uh, iterations 1 to 4 on one machine, so that they can execute in parallel to iterations 5 to 8 on the original machine. Then recursively this will go on. So now this will recursively spawn iterations 1 to 2, and so this is 1 to 2, and this is oops and this is 3 comma 4, and oops, let me just quickly redraw this, and this is going to spawn into 5 comma 6 and 7 comma 8, and this keeps going. So this 1 comma 2 breaks down to 1 comma 1, and then 2 comma 2, and so forth, right? Similarly, this breaks down into 7 comma 7 and 8 comma 8, right? So this is where each these leaf nodes, basically this is where each iteration has each loop has just one iteration to go. This is where the actual work will happen. So in this tree, until this point, right? So from the root to this leaf node, this is the work that we are doing in replicating the parallel for loop onto multiple processors in parallel. And at the leaf node, when every iteration has just one count to make, that is where the real work will happen. So this is the basic idea of what is happening in this matrix vector main loop. So notice the parameters, right? This is the input matrix A, this is the input vector X, this Y is basically the vector that we are trying to compute, n is the number of rows in input matrix A. Recall that A is a square matrix, and I comma I prime, this is basically indexes 1 comma 8, 1 comma 4, 5 comma 8, and so forth that we are passing here. So basically, assuming that your input matrix was 8 by 8 matrix, the first call to this matrix vector main loop would look like A comma X comma Y comma 8 comma 1 comma 8. The base case of this recursive function is basically when I is equal to I prime, right? So this is basically detecting that you have arrived at one of these leaf nodes, right? This is, you notice that when you are at 7 comma 7 or 8 comma 8, this is where basically I is equal to I prime. So this is where your iterate this outer for loop has exactly one iteration left, right? So that is where you compute this inner for loop. So this function, this matrix vector main loop is basically showing how to parallelize this lines 5 to 7. So only when I is equal to I prime, that is where you perform this work of the inner for loop. So this is happening at the leaf nodes, and in the else part, this is basically the recursive part. This is where if I is not equal to I prime, then you keep dividing and replicating, right? So you spawn the left half. So you compute the mid over here, and this is basically I to mid is the left half, and mid plus 1 to I prime, this is the right half, right? So you spawn the left half, and then you call the right half, and finally you sync over here, right? So both this left and the right half of the iterations can be computed in parallel because you're spawning them. All right, so here is basically a computation DAG, the computation directed acyclic graph that shows how our this matrix vector main loop, this function is going to be executed. So let's quickly understand what the strands are, right? So this black over here is basically the first strand. So this black node is basically the first strand, line number 1 to 5. This gray nodes, these represents the second strand, which is basically line number 6 to 7. And this white node, this basically represents a return statement. So you notice that we this matrix vector main loop, it doesn't have a return statement shown here, right? So let's say after this sync, there is some other line 8 which has a return statement and some minimum amount of work, right? So that is what is shown by this white node in all of these nodes in the DAG. So the order in which these computations happen are very similar to what we saw for the computation DAG of the parallel Fibonacci function in the class. So I'm not going to go into that again because it's exactly the same principle. However, notice that at the leaves you have this I equal to I prime, right? So you see that you have 2 2 comma 2 3 comma 3 4 comma 4, right, and so forth. So this is where at any leaf node is where you will actually execute this inner for loop, this inner for loop of the nested for loop. So which is basically this shown over here. So this is, remember that this is going to be O of n amount of work, right? Because this j is still going from 1 to n, and there is no parallel keyword here in front of this for loop, right? So this is still O of n. So let's quickly think about how much time it would take to fully replicate a given for loop, right? So let's say you start replicating a for loop which goes from 1 to n, right? So you start, for example, here so this is 1 to 8, right? So you're starting replication for a for loop that goes from 1 to 8. So you take, so you, for in the first step you divide it into 1 to 4 5 to 8, right? In the second step you 1 comma 2 3 comma 4 5 comma 6 7 comma 8 and so forth, right? So how many steps did it take before you reached the leaf nodes, right? So here if you see, it was basically so height of this tree is 1 2 3, right? It's basically 3, which is basically log 2 base 2 of 8 is 3, right? So if you are trying to fully replicate a loop that is going from 1 to n, it will take log 2 base 2 of n steps, right? So that would be essentially big O of log n number of steps for just replication. And then at this leaf node, in this case we are doing additional big O of n amount of work. So basically if we run this matrix vector function on a unicore uniprocessor machine, right, then it will take on just one processor. We have seen that this is going to take big O of n square, right, because of this nested for loop over here. However, if you had infinite number of processors, and let's say you can run it on in parallel, then in that case notice that we still are doing O of log n amount of work. So log n work is done for replication, and then after that at each of these leaf nodes we are still doing O of n work, which is basically this inner for loop that we are computing, right? So remember this for our next step, which is basically computing the work, the span, and the parallelism of this algorithm on the next slide. All right, so just as we have seen on the previous slide, work, you would recall, is defined as the time it takes to execute a given procedure completely on a single processor, right? So we have seen that if you execute that matrix vector multiplication function on a single processor, it is going to take theta of n square time. So that's the work. Now what is the span? The span recall is the time it takes to execute a given parallel algorithm on infinite number of processors, right? So that's t infinity n, and we just now analyze that it takes theta of log n amount of time to replicate the for loop on several processors, and then after that, once you have fully replicated on each CPU, you still have to do additional theta of n work for the inner for loop, right? So log n plus n is basically theta of n. So basically the span of this algorithm is theta of n, and work is theta of n square. So the maximum speed up, or in other words the parallelism, right, the max speed up or the parallelism is, you would recall, is given by the work divided by the span. So in this case that would be theta of n square divided by theta of n, which is basically theta of n simply. Okay, so that's the that's the max speed up of this this process or this algorithm. So notice that even when we are fully able to utilize the parallelism, even if we have infinite number of processors, all the parallelism that we would ever need to execute this algorithm, still it is taking theta n time, right? And this is happening mainly because recall that in the nested for loops we have not parallelized the inner for loop, right? We have only parallelized the outer for loop. So the next question is, can we somehow improve this code and maybe perhaps also parallelize the inner for loop? So would that help? So for example, if so, this is what we currently have, and let's say, so we recall that we have only parallelized the first for loop in line number 3, and then we have parallelized the outer for loop, right? So what if we modify this function, and instead of just parallelizing the first two for loops, also add a parallel keyword in front of the second nested for loop? Would that work? Well, we'll see. To answer that question about parallelizing the inner for loop in the matrix vector multiplication function, we must first understand what is a race condition. Right, so let's first start by defining the deterministic and non-deterministic algorithms. A deterministic algorithm is basically an algorithm that always does the same thing on the same input, right? So if the input remains the same, no matter how many times you run a deterministic algorithm, you will always get the same output. So for example, if you have a function that, let's say, just prints high, right? So no matter how many times you run this function, it is always going to print high. This is an example of a deterministic algorithm. As opposed to this, there are some non-deterministic algorithms that may give different results on different runs even for the same input, right? So the input has not changed, but every time you run them you may get slightly different answer. So here is an example. Let's say you're trying to run two threads t1 and t2, right? And let's say t1 says print x followed by print y, right? Whereas t2 says print w and print z, right? Now every time you run this threads t1 and t2, these are two threads that can run in parallel, and let's say that these are threads of the same process. So every time you run this process, these two threads can run in parallel on two different CPUs. Now depending on the order in which they execute or they finish, you will get slightly different output. So for instance, let's say first thread t1 completely executes and then thread t2 executes, right? So if this happens, you will get an output. You will first see x, then y, then you will get w, then you will get z, right? As opposed to this, if somehow t2 first executes and then t1 executes, then you'll see w followed by z followed by x followed by y. Okay, and similarly there might be some other interleavings of these x, y, and w and z, depending on how exactly these threads t1 and t2 are scheduled, right? So every time you run these threads or this process, you may get a slightly different output, even though you're running the same algorithm on the same input. So this is basically a non-deterministic algorithm, a very simple example. Now what is a race condition? So a race condition basically happens if, let's say, there is some shared memory. Let's say there is some shared variable a, and multiple threads are accessing the same shared memory, right? So let's say you have thread t1, t2, t3, all of them are accessing this location, the same shared variable a, and at least one of these threads is writing at a, right? So let's say this t1 says read, it's reading a, t2 is also reading a, but t3 is writing into a, right? So this is actually an example of a race condition. when multiple threads are accessing the same shared memory or shared data structure, and at least one of them is writing into that. Let's take an example to understand what might go wrong with these race conditions. So consider this simple code, this for loop over here, right? So for now, ignore this parallel keyword. Let's assume that this code is run sequentially on a machine. So in that case, what output do we expect? So this x starts as 0 and this for loop runs for 2 iterations. So if we increment this x, which was initially 0 2 times, we expect to get x equal to 2, right? That's the expectation. Now let's assume that this code is in fact parallel and it is run parallelly on two CPUs, or maybe as two threads on a multi-core or a multi-threaded CPU, right? So how would that? So let's assume this parallel code runs as two threads T1 and T2. Let's say T1 reads x equal to 0, T2 will also read x equal to 0, right? And let's say T1 is executing the first iteration I equal to 1, and this is executing the second iteration I equal to 2. Now both of them are going to do x is equal to x plus 1, right? And then finally basically after incrementing the value, they are going to write the value into x. So this simple instruction x is equal to x plus 1, it actually this is a high level language instruction which internally in the CPU might actually execute as a set of assembly instructions. So basically uh, whenever whenever a thread or a processor is trying to increment a value, it might do it in, let's say, 3 steps. So first of all, what it can do is it may, let's say, read the current value of x into its internal register. Then as a second step, it will increment the value of the register, and then in the third step it will, let's say, update this incremented value of r1 in again in the same memory location x. So the simple operation x is equal to x plus 1 is actually broken down into three assembly instruction steps. So let's assume that this is what happens in both these threads T1 and T2, right? So let's say T1 reads the current value of x in register r1. So let's say it says r1 is equal to x, then it says r1 is equal to r1 plus 1, and then finally it says x is equal to r1, right? And let's say what happens with T2 is T2 reads the current value of x in some other register r2. So it says r2 is equal to x, then it says r2 is equal to r2 plus 1, and finally it also says x is equal to r2, right? So this is how both these threads implement x is equal to x plus 1. Now let's see what different values of x we may get at the end if this code executes, right? So if the code of inside T1 and T2, it executes sequentially, right? So let's say T1 executes first completely. So basically let's assume that first we have x is equal to 0 here, and then we let's say if we first execute r1 is equal to x, then we execute r1 is equal to r1 plus 1, and then we execute x is equal to r1. So at this point, after, so r1 was initially 0 because x was 0. So when you incremented it here, it becomes 1, and then here when you say x is equal to r1, you get 1 in this x, right? Now after this writing has happened of in x, now if you start executing T2, so T2 will, instead of reading x equal to 0, it will read the updated value, which is 1, and then you will say in r2 it will get a value of 1, then it will say r2 is equal to 1 plus 1, so this will become 2, and then here when you write the final value, you get the value of 2 in x, right? So which is the expected value. However, there are some other executions of T1 and T2 possible, which will not always result in a value of 2, a final value of 2 in the x. So let's think about one of those scenarios. So let's assume that now T1 starts executing first, right? So x is initially 0. So first we execute r1 is equal to x. So here in r1 we get a value of a value of 0, and then let's say we execute the second step, r1 is equal to r1 plus 1. So now this r1 becomes 0 plus 1 1. Now before this T1 could update the value of x, this T2 comes and starts reading. As a third step, we execute r2 is equal to x. Now x has not been updated, so still x has the value of 0. So here we will get a value of 0 in r2, Next, let's say you execute this x is equal to r1. So now x is overwritten with value 1 because r1 was 1. Now you execute this as a fifth step, r2 is equal to r2 plus 1. Now because thread t2 has also read r2 as a value of 0, it will also compute 0 plus 1 1. So this r2 becomes 1. And then finally, as step 6, when it updates x is equal to r2, it again writes the same value 1 on x, right? So on when we execute this parallel for loop on two different CPUs in parallel, we don't get a final value of x equal to 2. We in fact end up getting a value 1, which is not the correct value. So this is an example of a race condition which may sometimes, for some it doesn't happen always, but for some interleavings or some executions of these parallel threads may result in an incorrect answer or an inconsistent output. So the same discussion has been summarized over here in this picture and the table. So let's now go back to our function, the matrix vector, the wrong implementation, where we have added a parallel keyword in front of the inner for loop as well, right? So having the parallel keyword in front of the first two for loops is fine. However, if you add a parallel keyword in front of this inner for loop, it basically gives rise to the race conditions similar to what we have seen on the previous slide. So essentially what would happen is there would be races on updating this yi in line number 7 over here. So essentially, instead of accumulating the sum of aij into xj for various iterations of this j, because now you are executing this inner for loop in parallel, different values of j would keep overwriting each other's values, and this the sum would not accumulate in this yi, right? So you will finally get an incorrect result for this computation, and that's why uh, just naively adding a parallel keyword over here will not work. So this is a very simple example of how it is easy to get an incorrect implementation which might look pretty efficient at first, but actually won't work in practice. So it is very important whenever you're writing a parallel code to make sure that your code is free from such data races. All right, so that brings us to an end of this discussion. I hope this was helpful. If you have any questions about this material, please email me or stop by. Thank you.